The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Presenter is Dr. Mohamed Moustafa. He is an assistant professor at the Department of Civil and Environmental Engineering at University of Nevada, Reno. His main areas of expertise include multi-scale experimental testing, structural design for mitigating hazards, and finite element modeling with application to infrastructure and resilience of built environment. Before joining UNR, he did a short postdoc at UC Berkeley, where he also completed his master's and PhD in civil engineering at UC Berkeley. Without further ado, Dr. Moustafa.
All right, good morning, almost good afternoon, everyone, or almost noontime. So thanks for attending this, and thanks for Dr. Alam for putting these always interesting sessions here. So my presentation today actually is about probabilistic study. I'm sorry. Okay. It's just a probabilistic study actually to investigate the effect of damping modeling as part of evaluating actually our bridges, or using any of the performance-based design frameworks like the one that Dr. Alam was just explaining in the previous presentation. Usually nonlinear time history analysis is a key component of doing these sort of analyses or assessments. So what we wanted to study here, using again a probabilistic study just to develop fragility curves, how would our modeling characteristics affect the outcome, or basically the final product which we use for performance-based design, mainly fragility curves. How would our fragility curves be sensitive to the modeling of, or the different damping modeling characteristics? So that's the title of my presentation. I have a student working on this topic. So most of the work that I'm presenting here is actually what he's doing for as part of his PhD, not the full PhD. And so it's an ongoing study. So the outline actually for my presentation today is just few, a brief introduction, not about performance-based design, just about modeling now of damping particularly. I think during the first two presentations, you have already been introduced to performance-based design for bridges, at least how people are approaching this. What are the objectives of our study here? The bridge that we are using and how did we model it, the ground motion records that we used for all our fragility assessments, and some preliminary results, as I mentioned, and conclusions associated with these results. So just damping is that's my interest here, or the focus of the topic here. How do we model damping actually? And damping is, in general, one of the key characteristics of your analysis. So if you just use a wrong assumption for your damping, this definitely will affect the results. So the most popular, or the most typical method for modeling damping is the Rayleigh damping. And the Rayleigh damping, what you're doing actually, you're just building a damping matrix that is a mass proportional and a stiffness proportional. Based on the assumption that you have, basically for the Rayleigh damping, as we'll see in the next slide, you can have different effects. So the Rayleigh damping in general, you just have a component that's mass proportional, a component that's stiffness proportional, and you define, to calculate the Rayleigh damping coefficients, you need to identify two frequencies that you use. So these two frequencies can be just the frequencies of the first two modes. It can be the first mode and the 10th mode. So this is one of the parameters that we studied here in this exercise. So I'll be talking about this later on. But in general, the dash, what you see in dash, these are the stiffness only proportional or the mass only proportional. The Rayleigh damping is just the solid curve, this, that you see, which combine both. Based on the definition of omega I and omega j, this is the two frequencies that you use to calculate your coefficients. So if you are using two, basically, the first two modes, then all the higher modes, you'll just have extra damping, way more damping than what you anticipated. So if you have a higher mode effect, which we will see in a few minutes or in a few slides, you might just be using a false damping force that's not necessarily reflecting the real thing. So these are the main characteristics of the Rayleigh damping, whether you want to be mass only proportional or stiffness only proportional, or which modes you use basically in calculating the damping coefficient. These are the three things that we are studying here. So if there is such assumption, why Rayleigh damping is still so appealing? It's actually very easy. You don't really need to build a stiffness, a whole new matrix. You just use basically your existing stiffness matrix and existing mass matrix. And what people have been doing in the bridge, I mean the building side of research, they have been trying to identify damping. Maybe they did a little bit more work on this than what we have been doing in the bridge engineering, like business of things. So some recommendations to avoid false damping forces, for example, is just to eliminate the mass proportional part and just go with the stiffness proportional part of the damping. So these are the sort of the things that we are studying or looking at here. So we still don't see, to the best of our knowledge, in this study, we don't really have a very solid guideline. If you want to go and do like time history, nonlinear time history analysis for your bridges, how would you model your damping? The typical, using Rayleigh damping, was 5% damping. Just use maybe the first two modes to calculate the coefficients. Maybe this is a typical assumption. How this assumption might, like lead to different results if you vary any of these the parameters. So since there is no guideline or like a solid reference, same thing for buildings also, like, most of the damping modeling guidelines are just subjective, so you can adopt them, you can just use a different assumption. So what we are trying to do here eventually is to have some sort of a reference, and if not a reference that gives you a recommendation for what model to use for damping, at least to know what are the consequences. If you are using 5% damping versus 2% damping, what you should expect in terms of the final product, again, that we are looking at in this particular case is the fragility curves. How would your fragility curves be affected based on your modeling assumptions? So that's what we are trying to provide here. Again, not a guideline, what's correct and what's wrong in modeling damping. That's not our objective. The objective is just to, based on the consequences, show you the effects, and it will be a reference for the designers or the engineer to eventually make a decision based on that they can observe from a study like this. We will see actually also the recommendations that we receive all the time from the buildings, like industry, in terms of like eliminating the stiffness, I mean the mass proportional part of damping, or using a tangent versus an initial stiffness. So as we have seen in the previous slide, a key component of the Rayleigh damping is actually a stiffness proportional. So what type of stiffness matrix should you use here? Is it the initial stiffness or the tangent stiffness? These also lead to different consequences, and many of the building studies recommended, in some cases to use the tangent stiffness, not the initial one. So we are also looking at the differences here. And the last thing is to look at this at the system level and the component level. So not only at the final fragility curve, or the overall fragility curve of a particular bridge, but also we are breaking it into components, primary components and secondary components, and see how each of these components basically is more sensitive or less sensitive to damping assumption. So what we are doing here, that's a pure analytical study. So what we eventually will have, we are doing a whole bunch of analyses to get some fragility curves. So the modeling assumptions that we are varying here for the damping, we have 4 different type scenarios for the damping that we are looking at. If you're just doing Rayleigh damping, and by Rayleigh in this context means both the mass component and the stiffness component, but using the initial stiffness, or if you use Rayleigh damping with tangent stiffness. And the second, like type, or which will lead to the third and fourth cases, is basically if you eliminate the mass contribution and just go with the stiffness proportional part of damping, again with an initial stiffness or a tangent stiffness. So these are the 4 scenarios that we are like studying here. For each scenario, we have studied 3 different damping ratios, 2%, 5%, and even 10%. Some cases, like some duties like Caltrans for some configurations maybe to account for the extra damping or energy dissipation at the abutments from the soil, they can allow you to use up to 10%. So this is, of course, very few cases, but at least we wanted to study also how this would make a difference. And the last thing that we studied is what are the 2 frequencies that you use to set up or to lock your Rayleigh damping coefficients early on. Are you using only the first modes, the 2 modes, or maybe the first mode and the 10th mode? So these, again, we looked at. Eventually, what we are doing nonlinear time history analysis and develop fragility curves. So this, for a 100 bridge cases that we have, and of course that's the probabilistic nature of things, is that we are varying randomly the parameters of the bridge to some extent and randomly matching it with 100 ground motions. So every ground motion is randomly paired with a bridge model, and we have been doing this for 24 cases for damping. So we ended up with 2,400 analysis cases that I will be showing the results briefly here. So the bridge that we are looking at is mainly older types of bridge. So our assumption here is that mainly, or maybe important applications for performance-based design or current needs for performance-based design for like bridges would be running like an assessment of existing bridges. So if we want to make a retrofit decision, maybe instead of just going back and check the force-based design or a displacement-based design, maybe you can run it through a whole performance-based design framework to see how would you make your retrofit decision. So accordingly, we prefer to go with slightly older type of bridges, not recent ones. So the bridges that we are using here is mainly for the, I would say, the pre-Northridge era. So for those who are like familiar with the bridge engineering here in the US, of course, most of you, I'm assuming, are familiar with this. The Northridge was one of these key events that changed significantly our design codes. So what we are doing here is the pre-Northridge era, where the design was mainly not evolved as now. And what we looked at is a particular type of bridges, which is the multi-frame. Also, we are looking at both system and components. So to make sure that we capture critical components, we use the multi-frame bridge configuration, not a single frame. And by multi-frame here, we mean you have at least one in-span hinge. So the in-span hinge will lead to two independent frames. So pounding at the in-span hinge, unseating at the in-span hinge, these are one of the basically possible scenarios for damage that we are considering here. Just again, some more information about the bridge characteristics. It's a 4-span multi-frame. And one multi-frame, again, it has one in-span hinge that we are using here in this case. This is the before, 1971 design era for the bridges that we are using. And all the other things evolves accordingly. The lengths for the overlap at the deck, at the abutment, at the in-span hinge, all these things evolves accordingly. And here we have also some more information, like the pile caps, for example, that we modeled it, the soil. So we have, in the next slide, actually, we'll show this. So that's the model, the OpenSeas model that we used. It's a 3D model. Technically, we are using 1D elements, but the model is a 3D model, as you can see here. So we try to accurately capture as much as we can from the components that might fail. It's all the way through, the piles, the soil itself, and the soil not only at the piles, so that we can capture the soil structure interaction, but also at the abutments. So all these springs that you see at the abutment sides is mainly to capture the failure that might happen as well in the soil. So we try to be comprehensive in terms of all the the components that might fail. Again, we are looking at not only the system fragilities, but we are looking at both a system fragility and component fragility. So we wanted to capture as much or as many components as we can here. So this was the bridge, and of course, just going back one slide again, I'm sorry. What we are doing here, you have the configuration for the bridge, but we still randomly vary some of the parameters, how many columns you use per pier, the spans. These are the random variables that we use. So we eventually, this is a typical configuration, but we were able to generate 100 different bridges out of this configuration. For these 100 bridges, each bridge was randomly paired with another 100 ground motions. So the 100 ground motions that we used for this analysis were basically selected from the PEER, the Pacific Earthquake Engineering Center database, which is getting almost very popular now, especially in California. We're here in California, actually. So most of the studies in California particularly are using this database for all their ground motions. 20 particular ground motions out of these are near fault, so that we account for the pulse and pulse-like ground motions. We have basically our selection criteria is just to choose shallow crustal earthquakes. Again, every time you change your set of ground motions, you can have a different results, but we just try to select something that's typical, or at least representative of a typical California bridge. This was our objective here. So again, these are some of the variables that we changed for the ground motion selections. The vertical component, I have to mention this because this is, again, one of the most popular topics that people always ask, did you include the vertical ground motion effects? In this study, we didn't. So we are just using biaxial, the X and Y components of earthquakes. So starting for some results, basically, I jumped right away to the fragility. So what we are doing the nonlinear time history analysis, but eventually we just get for each case we just fit, basically we get the damages, we arrange the damages, we fit a log normal distribution to get our fragility curves here. So what I'll be showing is mainly the fragility curves, the products that we are after, and see basically how these fragility curves are sensitive to the different damping characteristics. So 3 things that we are looking at: the effect of the frequency range, and by the frequency range, I mean which 2 or values you used for your frequency as part of calculating the Rayleigh damping coefficients. Are you just using the first 2 modes, or the first mode and the 10 mode? So these are the 2 different things that we choose here, either just using the first 10 modes or the first 10 modes. And when you, based on this selection, what you are doing, or based on the curve that we have seen early on, this is the range where you almost lock your damping ratio at the value that you choose. So if you want Rayleigh damping for a 5% damping, this 5% damping pretty much will be just between these 2 frequencies that you choose. Before this, which is, you don't care, it's out of the range, but after this, especially for the higher modes with larger periods, you might have, if you remember, the curve is shooting up. So outside this range, if you're looking at, or if you wish to look at 5%, Higher modes, if you're not accounting for this, might shoot up to 10%, 20% damping. So you are even using false, or a spruce-like damping forces. So what we're doing here, 2 modes versus 10 modes, and this is some of the fragilities that we get. So the first one that you see here is the system. So some good news here is that for the 4D, the scenarios that we're looking at here, the 2% or the 2 modes versus 10 modes, is that the change is not very significant at the system level. However, we can see when we go to the deck unseating, so these are the system level, the column. The first one is the system, the second one is the column. The third and the fourth are the deck at the in-span hinge and at the abutment. So we see here that the most risk in general, regardless from the damping, is the deck unseating. And this is a very, alarming actually, or like a red flag for older bridges. Most of the older bridges use, 10 maybe to 15 inches for overlap. Sometimes it can be as small as this for the seat. But now with the newer codes and with the newer guidelines, this has been resolved. So we still don't know if we using a new code, is this overlap that we provide at the seat, at the abutment, is it, or at the in-span hinge, is it enough or no? That's a part of the study. I'm not showing it here, but it's part of the study as well to look at the newer codes. But we can see here that deck unseating is very sensitive to damping, and in the overall scheme of things, it's also the most vulnerable component here. We did the same thing for the secondary components, and for the secondary components, again, going back to Dr. Al-Lam's presentation, you have seen that we usually define damage states, or the target objectives basically for your performance. So we have a slight damage change state, a moderate damage state, a complete damage state, and so on. So what we usually see for the system and the primary components, these are the components that fail or designed to fail, that you wish where you lump all your ductility and so on, like the columns. These are the primary components. So primary components would usually go all the way to a complete collapse or a complete damage state. However, for the secondary components that we considered here, like yielding in the soil and things like that, rotation at the foundation, these are secondary components. We are not expecting, or we are not allowing actually our bridges to fail in these modes. So what we would experience here would be just a slight or a moderate damage state. So we are not expecting to see a complete damage state or a severe damage state for these secondary components. So the idea again to see or to get an insight how our modeling characteristics will affect the different fragilities for the different components. So we can see some components are less sensitive than other ones. So this one here, again, going to the displacement at the in-span hinge is pretty much the most sensitive to the damping. And by the damping, just 2 versus 10 modes here that I'm showing. Another way of summarizing things, this is just the median fragility, like the PGA value at your median fragility. We can see here again the 2% or like the 2 modes versus the 10 modes for each of our assumptions. And these are the different damping ratios. I will talk about this in a minute. But we use 2% and 5% and 10%. So if you are comparing, actually, I don't know if you can see the cursor here. Probably not. But if you just compare, let's say, using 10 modes versus 2 modes at the system level, the first very plot, you might see that the differences are not that big. But again, when you go to the plot C or subplot C, which is the deck unseating, you can see that the median fragility, which is somehow express how vulnerable your component is, deck unseating, again, you can see very large variations when you change the damping characteristic, or this particular damping characteristic, which is using 2 modes versus 10 modes in calculating your damping coefficients. Again, this is a table to summarize things. I'm just showing the same results here, but in a very different way. So what we are doing here, if we want to compare everything, again, is the typical. I'm just quote unquote here. Typical is just Rayleigh damping with like the initial stiffness and 2 modes and 5% damping. If this is the typical damping characteristic, how actually our cases, when you vary this, would compare to this datum or our typical case. So you can see here at the system fragility, we can see up to 20% change at the system fragility. And again, going for the deck unseating, I don't know if you can see it from here or no, 180%, up to 180% change from the typical case. So you might just go with a completely different response just by using this damping assumption or a different one for the deck unseating. The other thing that we looked at is the effect of the mass, proportional damping. So if we just run, again, the same analysis, but using only the stiffness proportional part of the matrix. Why we are doing this? As I mentioned earlier, these are recommendations that people developed mostly from the building, industry, not from the bridge industry, but in the building industry, a lot of recommendations came that to avoid the spruce or the false damping forces or extra damping forces that you don't need, it's better to go with the stiffness proportional. There is no physical, like underlying meaning for most of these damping assumptions anyways, but we just try to see what would be the effect if we ignore the mass contribution. So we see again that the system is somehow changing the system fragilities, but not as much as you would see in the Dick unseating, for example, again. These are the secondary components, and we see now that some secondary components are even less sensitive, but the displacement, for example, is the only one that is pretty much sensitive to the changing or the ignoring of the mass proportional part of damping. The last thing we looked at it is the 2%, 5%, and 10%. So again, these values are just recommendation. Like we know that damping is not something that you just go and calculate from the dimensions of your columns, for example. So why you are using 5%? This is the recommendation based on some like system ID studies and a whole bunch of data that have been collected, and they came up with some recommendations for reinforced concrete, use this much damping ratio, for steel, use this much. So there is still a range. With all these studies, there is still a wide range for the damping ratio that you would use. Some would recommend 2% only for bridges because you don't have really too much, or several non-structural components that would dissipate energy as you would have in a building, like tall buildings with the windows and the facades and everything. The curtain walls, these dissipate more energy than what you typically have in bridges. So some recommendations, and again I say recommendations because there is nothing in written or in code here, that 2% would be appropriate to use for bridges. Maybe 5% is a little bit on the higher side, but we went all the way to 10%. Why? Because as I mentioned, one example, Caltrans, as an example, they allow to use 10% for special cases. Single span bridges, when you have contribution from the soil, is expected to be large. So we try to look at the differences, and we find, of course, that 2 versus 5 versus 10% would lead to, this is the medium fragilities again that we're comparing here for the 4 damage states that we considered. So this is the PGA value at the median, sorry. So of course, to achieve the full collapse or the complete damage state, you will have, this will happen probabilistically at a larger PGA value than the slight the damage state, for example. That's why you see these 4 are almost varying linearly. But just take one of them, one case. This is what we are comparing here. These are 3 different damping cases to see the effect of the 2% versus 5%, and we can see differences as well. So based on this, again, we cannot recommend what's good or what's wrong, but at least we provide a preliminary tool for the engineers to know if I'm using 5% damping, then I should expect that my system fragilities should be within this range if I use 2% or 10%. So it's up to the engineer to make the decision eventually. At least this is a preliminary tool to identify, and this is not a complete study yet. Hopefully you are working a little bit more to include more cases, but the objective will be to provide these as a design tools or design basically recommendations for the engineers to eventually go and pick their own damping assumption based on what they want to do for their analysis cases. So just to wrap up, these are some quick conclusions that we see here, is that in general, components and system fragilities have different sensitivity to changing the damping characteristics. So we have seen that the system, for example, is less sensitive than the deck unseating. Some other components are even less and less sensitive. So that's something we observed. The higher mode effect, this was very particular, especially for the deck unseating, that was we observed almost 100% change just when used 2 or 10 modes in calculating your Rayleigh damping coefficient. So it's really important to know if you're expected basically or expecting to have a higher mode effects in your bridges where you have higher modes of vibration are included, then it's better when you are calculating the Rayleigh damping. And this might sound obvious, but honestly, people might just overlook this because not everyone is just going to pick the frequency of the 15th mode as part of calculating the Rayleigh damping coefficient. So just, if you're using OpenSeas, you use the default, maybe the first 2 modes, and that's it. So it's worth, just slowing down at this step and say, basically think a little bit. You can look at your model analysis, how many modes you think, are contributing, and calculate your damping coefficients accordingly. The system fragility is more sensitive to ignoring the mass proportional than the components. Some components are less sensitive, which is a good news, actually. And then the Rayleigh damping with initial stiffness versus the stiffness damping only. With tangent stiffness, these are, in terms of ranking, the highest and the lowest sensitivity to changing the damping ratio. So if you are decided to go with the Rayleigh damping with initial stiffness, you should be prepared that this is very sensitive to your modeling assumption. However, if you're using just the stiffness proportional damping, this is less sensitive. And then the final thing that we observed here is deck unseating. I keep saying deck unseating. You have heard me saying this like 15 times at least today. It's just for older bridges, this is a very critical aspect, and it's a red flag. So if you are doing a retrofit, like for an older bridge, and you decided to do a performance-based design, performance-based assessment or evaluation, and part of this will inquire or entail some nonlinear time history analysis, then you should be really focused on what you want to do for your damping, because your results will be much sensitive to this. So with this, I would like to thank you, and I'll be happy to answer any questions.
Mohamed, thanks very much for this nice presentation. So my question is, so you have this Rayleigh damping, you're looking in a nonlinear time history analysis. So how generalizable do you think these results are if somebody would want to model a different bridge or use a different modeling approach? Because ultimately this is mass and stiffness proportional damping, right?
Yes.
So if you change completely the stiffness matrix or the mass matrix, which will depend on how you model your bridge, right? There's a lot of nonlinearity that you're presenting there at the soil level between the two decks at the gap and so on. So how do you think these results, if they're generalizable to other bridges, or if you were to use some other modeling approach?
So I think, thanks a lot for the interesting question. So what we are doing, actually, we just focus on one class of bridges. So I agree, of course, that changing the bridge characteristics, or at least the type of the bridge, would change the mass and stiffness. But what we were doing as part of our probabilistic framework, these 100 bridge models that we generated, they have different geometries and different spans, so somehow to account for the mass and the variation in the mass and the stiffness, but within this class of bridges. So we didn't look into different materials, we didn't look into different type of bridges without let's say in-span hinges. But I agree, this of course changing at least the broad class of bridge will lead to different observations. So before we go ahead and make a general observation here, and that's why this is just preliminary, because we're looking at actually 4 different classes of bridges. Yeah, the overall conclusion will be tied, hopefully, or generalized based on different types of bridges, not only one type of bridge. Any other questions? Thank you.